I'm going to be talking about a number of things, but the bulk of it is going to be work done with Dan Kapatz, a student on his way to, at Harvard on his way to IAS, Malcolm Perry, a professor at Cambridge, Ana Reclario, a student at Harvard, and myself. We made a conjecture about quantum electrodynamics and infrared divergences and sort of proved it to leading order last spring. And just in the last 2 weeks, there's been a complete proof by Choi and Akori. And as usual with most projects I work on, it ends up being about black holes in the end. So if there's time when we get to the end of it, I'll say something about black holes. So in the last few years, there's been, I've written a book about this, which will appear in March, a triangle that governs the infrared sector of the world around us. And the top of this triangle is the so-called soft theorems in quantum field theory. One corner of it is the so-called memory effect, which LIGO is actually rather optimistic about now. Recently, they've become optimistic that they will measure this in the next few years. Certainly, it will be measured in gravity in the next few decades, and there are discussions about measuring it both in quantum electrodynamics and in quantum chromodynamics. And over here, we have asymptotic symmetries, or equivalently, conservation laws. And these are connected in straightforward ways. The simplest one is this. It's just a Fourier transform. This one is a word identity. And this one is a vacuum-to-vacuum transition. Memory effects measure transitions. Gravity, gauge theory, and non-abelian gauge theory, when they're not confined, or Higgs, have degenerate vacua. And the memory effect measures the transition from one vacuum to another. Now, this is all about infrared phenomena. And one of the salient infrared phenomena that many of us encountered in 4 dimensions is infrared divergences. And so in the first year quantum mechanics, you learned about the quantum state and unitary evolution. And then the first semester of quantum field theory, you learn about scattering, amplitudes. And then somewhere in the middle of the second semester, you're suddenly told, but wait, scattering amplitudes don't exist in QED. We can't talk about scattering amplitudes. We can only talk about inclusive cross-sections where we sum over soft photons below some threshold. And when I heard this, when I was a graduate student, it bothered me for a little while. Well, what's wrong with, why can't we just talk about the unitary evolution of quantum states? Why don't we have, it's not really quantum mechanics anymore if you're computing probabilities. And, but then there's a beautiful story about how it's all self-consistent, and I quickly forgot about it and went on to think about other things. But I think that situation has become that there isn't such a thing as a scattering amplitude in all the theories we're actually interested in, has become more disturbing recently when quantum field theory is something rather different now than it was when I was a graduate student. When I was a graduate student, it was a device for predicting results of experiments. Now we are very interested, as this conference exhibits, in properties of quantum field theories and scattering amplitudes as mathematical objects. And if the scattering amplitudes themselves generally don't exist, what are we talking about? So, so the question that we asked in this paper is, does this recent insight into the infrared structure of gauge theory tell us anything interesting about how to think about the infrared divergences? And the answer, which I will explain in this talk, is yes, they do. And the answer is that there are no infrared divergences in quantum electrodynamics. And also we now know in perturbative quantum gravity. And I'll make this more precise. Now, I want to stress at the outset, just to be clear, quantum electrodynamics is the most amazing theory in the history of human thought. It's been tested to 16 decimal places. I am not in any way suggesting that anybody ever, well, I'm sure people did say wrong things, but I'm not questioning the huge body of literature or the fantastic agreement between theory and experiment. I am just finding a new way of looking at old things. And it's, moreover, a way of looking at old things which in other subjects, like Yang-Mills and gravity, suggests new things that we don't yet know. And even quantum electrodynamics, it suggests new experiments that we might do that, that will test the theory in different ways than we've tested it before. Okay, so the outline is that I'm going to sort of rederive and generalize something which you don't learn about in the second semester of quantum field theory, but depending on who your teacher is, you might get to it in the third or fourth. I never got to it. The so-called Faddeev-Kulish, and there are many other names attached to this, Kibble, Chung. IR finite scattering amplitudes. But from a modern perspective. That's going to be most of the talk. And from there, if there's time, I'll motivate two conjectures, one for Yang-Mills theory and one for black holes, that are suggested by the kind of new way of thinking about things. Okay, now, I'm going to start by giving a kind of lightning review of something which I've been talking about for a few years now, and that's the fact that in ordinary quantum electrodynamics, there are an infinite number of conserved charges, which generalize. We're all familiar that in any scattering process, the total net incoming and outgoing charge are equal. But this is, in fact, just one of an infinite number of charges that are conserved in quantum electrodynamics. And again, it's something that we knew about, but we didn't really say this way, or we knew about it implicitly. So I'm going to draw a picture of Minkowski space, which I will save, because I'll refer to it throughout the talk. So here's a Penrose diagram from Minkowski space. This is future null infinity, the place that light rays go to. Past null infinity, where they come from. Now, the boundaries of past and future null infinity are actually very important places. And so I've given them names. Scri plus minus, the past boundary. Scri plus plus, the future boundary. And then we have scri minus plus. These are not the same thing. And we also have scri minus minus. And then up here, we also have spatial future time-like infinity and past time-like infinity. And I'm going to use U as a retarded coordinate at future null infinity, and V as an advanced coordinate on past null infinity. And if I hold U fixed and take R to infinity, that's a null line that goes like this. So fixed U, R going to infinity, you get out to null infinity, not to spatial infinity. And then there's something, this is 2 of the 4 dimensions of Minkowski space. And then there's a sphere which has become known as the celestial sphere. And I'm going to use Z and Z bar for coordinates on the celestial sphere. OK, now, let's suppose that we have just one electron sitting in the middle of Minkowski space. Then there'll be a constant radial electric field. And it will be constant. Its magnitude, the radial component of the electric field, will be constant at infinity. And it will be equal at scri minus plus and at scri plus minus, of course, because it's just a constant. In other words, if you take the radial component FRU and move it down to here, it agrees for a stationary electron with what's up here. But now suppose we boost it so that the electron has a world line that will look like this. Electron's a massive particle, so it goes from past time-like to future time-like infinity. Something very odd happens, which Maxwell certainly, or at least Leonard and Vikaard knew about, but I was confused about until the last few years. The radial component of the electric field becomes discontinuous here. In other words, if you go up here and go back down to here, you don't get the same thing as if you go down here and go up to here. And instead, I'm not going to work this out in detail. It's all in gory detail in my book or in most of these papers. The statement is that there is matching conditions for the electric field. And basically, it becomes discontinuous because the Lorentz transformations themselves are discontinuous at this point. A boost will boost up this way, but out that way. OK, so what does happen is if we take FRV at scri plus minus, and at some ZZ bar, that's equal to, that's in the past, FRU at scri minus plus at the antipodal point. That is, the radial value of the electric field here is equal to at the bottom at scri plus minus is equal to the radial value of the electric field at the top of scri minus. OK, now it's a little annoying to put these antipodal things all over the place. So I'm just going to adopt the convention that the Z and Z bar that I use in parametrizing celestial spheres that go to past null infinity are antipodally related to those at future null infinity, which is just a notational sleight of hand which enables me to erase this. In other words, I'll think of the identity between the past and the future as always involving this antipodal map on the sphere. Okay, so now let's define a charge associated with the future, which is Q plus of ZZ bar is equal to FRU of ZZ bar at scribe plus minus. And by this continuity condition, it's equal to Q minus of ZZ bar, which is equal to FRV of ZZ bar at scribe minus plus. Now we can use Gauss's law and integrate by parts these Q's. And we find, using Gauss's law, that Q plus is, let's imagine now maybe we have some currents, some charge currents which might be passing through null infinity. Now, I'm going to go back and forth a little bit here. Right now, I'm going to have all my charges go out to null infinity. Now, in the real world, electrons don't go to null infinity. They go up here. But notationally, you come to the same conclusion, but the equations are longer. So to simplify things, for most of the time, I'm going to pretend like all the charges go out to null infinity, which would happen in a theory with massless charged particles. And at a couple of points, I will say what happens in the massive case. All right, so we can write Q plus as equal to, integrating by parts and using the constraints, it's equal to a soft term. So what do? We just integrate by parts, and we take du FRU, and then we use the Maxwell constraint equations, which will relate that to the charge flux and the other components of the Maxwell field. So Q is equal to a soft piece and a hard piece. And the soft piece is equal to the integral from minus infinity to infinity du dz. So this dz is the covariant derivative of, with respect to the unit metric on this celestial sphere. And I've rescaled to eliminate some powers of r. dz fuz plus dz bar fuz bar. Why do I call this a soft part? Well, because it's a zero mode of something, and it's linear in the electromagnetic field. And then the hard part is just equal to the integral from minus infinity to infinity du of the charge current Ju. And in my usual conventions, there's an e squared there. Okay, now notice that Q plus S, if we work as is natural in the gauge where AU is equal to 0 on the boundary, Q plus S can be written, it's just a total derivative du AZ. It's the difference between dz AZ plus dz bar AZ bar at scribe plus plus and scribe plus minus. Now, we're assuming that everything is at the boundaries of scribe. There's no radiation. So the electromagnetic field must vanish. but that doesn't mean that A vanishes. A can be any flat connection on the sphere. So the soft part of the charge measures the difference between the flat connections on the sphere. So there's a different flat connection at the bottom of scribe plus as there is at the top of scribe plus if anything interesting happens. And that is the ultimate origin of the memory effect, and that's what the memory effect measures. And the fact that flat connections must be regarded as an equivalent is what tells us that there's an infinite vacuum degeneracy in electromagnetism. And the same thing is true on scry minus. Now, I'm sorry, my handwriting's terrible. Ju is charge, matter, current. So if it's just pure electromagnetism, it vanishes. But if there are charges going through null infinity, you get that. Now, there's also a story if the charges go up to scribe plus, and you still have a hard term, which is related to kind of an ADS bulk to boundary propagator to the, well, I'll give a formula for it later. But QH is non-zero. But notice when I integrated by parts, I didn't include a boundary term at the top of scribe plus. I assumed there was nothing there. OK. Now, obviously, Q plus is equal to Q minus. That's the matching condition I wrote there. And in fact, we can write in, and we can take them in the quantum theory, we can take the matrix element of this, and we have out Q plus S matrix, Q minus in is equal to 0. That's the quantum version of this classical conservation law. And OK, so this is an infinite number of relations, one for every z and z bar, one for every point on the sphere. We could also, of course, integrate these over the sphere and have the q's depend on functions that we integrate against. And this is the soft photon theorem. So we could have turned the whole thing around. We could have started from the soft photon theorem and proven that there are an infinite number of conserved charges in electromagnetism. So that's why I say this is something we knew all along. We've known about the soft photon theorem since maybe 1937 or 1965. I don't know when we've known about it for a long time. But the fact that it's simply a conservation law that follows from matching at infinity is a new observation. All right, let's use this to do something. Let's use this to compute. Let's use this scattering amplitude to compute something. Let's compute Bhabha scattering. So Bhabha scattering is E plus E minus going to E plus E minus with no inner-out photons. So here's a picture. And again, I'm going to make the electron and positron massless just to simplify the discussion. I'll talk about the massive case in a moment. So we have incoming electron, incoming positron, outgoing positron, outgoing electron, and no photons. Now we have to solve the constraint equations, and let's look at the constraint equations on scribe plus. So on scribe plus, we have the constraint equations say that du FRU, that's the Coulomb part of the electromagnetic field, plus the divergence of the radiative modes, is equal to the current. This is the constraint equation up here of the Maxwell thing. OK, now in Bhabha scattering, there's no radiative modes. there's no in or out photons. So these things should be thought of as 0. And now we want to say that the electromagnetic field vanishes in the far future. And it should also vanish in the far past. And so if we want to solve this, so we see we have du FRU. It's 0 here, but it's 0 here. But when we come down, when we hit this positron, we get something non-zero. So we'll have FRU not equal to 0 here. There'll be a line of FRU. I'm making everything a delta function. I could smooth it out, but that's not really important. So there's a line of FRU will be non-zero here. It will also be non-zero down here. And same thing if we have FRV non-zero here. It will be non-zero up here, and it will be non-zero up here. But these lines of Coulomb fields, if there's any non-trivial scattering, these lines of Coulomb fields are not going to meet if there's any non-trivial scattering angle. So this matching condition is going to be violated. Therefore, this amplitude is exactly 0. And we concluded this just from the constraints at infinity. Now, this is not a new result. This is an old result. It's well known in quantum field theory that Bhabha scattering is 0, but it's usually said in a rather different way. And the way it's usually said is that you start by computing some scattering, which, for example, would have a diagram like this. Or in fact, we just have all possible Feynman diagrams in here. And then we start adding things like this, where we attach soft photons to external legs. And this actually is infinite because of infrared divergences. And then we see, oh, but there's even another infinity where we exchange 2 soft photons. And we continue along these lines, and we add this up, and we find that we get e to the minus infinity. Therefore, Bhabha scattering is 0. So what I would say here is that the role of infrared divergences in the usual computation, in the usual Feynman diagrams, is just a ingeniously clever trick by the Feynman diagrams, who will never make a mistake on you, to set to 0 something which had to be 0 because of the conservation laws. And so there are no real infrared divergences in quantum electrodynamics. They just appear if you try to compute something to correct your error, if you try to compute something which should be 0. But now I would like to compare some things which are not 0. Not everything should be 0. There should be something which is not 0. So we see that the problem over here is that we had these Coulomb fields which extended all the way down to here and violated the matching conditions. We could have avoided that by exciting some radiative modes and letting them solve the constraint equations. So let's do that. So instead of setting these terms to 0, let's set the first term to 0. Let's not have any Coulomb fields at all. And then we have, so we have du FRU, but we're going to set that to 0. And now we have dz FUZ plus dz bar FUZ bar is equal to minus e squared. I've got the factors in here. Sorry, I didn't have them before. And let's have that be some source which comes out at retarded time u minus u0 at the point z minus z0 on the celestial sphere. Okay, now we can solve this equation, and we can solve it with az is equal to minus theta of u minus u0 over 4 pi z minus z0 e squared. Notice that this A, if we Fourier transform it to frequency space, has a pole. The Fourier transform of a step function is a pole. It has a pole at omega equals 0. Moreover, this A is pure gauge before and after u equals u0, but it's different. It's a different pure gauge. So there's been a shift. This A represents a shift in the flat connection on the sphere. And so it's telling us about a shift from one QED vacuum to another. So that is AZ scribe plus plus, AZ scribe plus minus is not equal to 0 in this example. So this solves this equation. And now we can make a dressed quantum state. Let me call it psi dressed, which is equal to e to the minus I e squared over 2 pi d squared z over z minus z0 a z bar of u0 zz bar plus Hermitian conjugate acting on the charge state which comes out at charged particle which comes out at uz0. So this is a hard charged particle dressed by some photons which include a soft pole. Now this particular state looks like a shock wave which comes out at u equals u0. So it actually has UV divergences. The shock wave is infinitely thin, so it has infinite energy. We could easily spread that out, but we're not really interested in UV problems here, so I'm just going to ignore that. And you can check that this state is annihilated by the operator versions of the constraints without entailing any expectation value for FRU. And moreover, the Coulomb field is sort of shielded now by this soft cloud that I've added. Let me add this to dress all the states, put soft clouds around them. And then there will be no Coulomb field. We'll have FRU equals FRV equals 0 at infinity, and there will be no problem with the matching conditions. And the infinity of conservation laws are trivially satisfied. No Coulomb fields whatsoever at infinity. Okay, now, it turns out that the scattering amplitudes for these states are infrared finite, and that this was shown by Fadeev-Kulish way back in 1970. What I've constructed through a roundabout argument is a dressed Fadeev-Kulish state, and they showed at that time that all the infrared divergences were canceled, and secretly they were including a shift in the vacuum state, though those words were never spoken. Now, one thing I want to say about Fadeev-Kulish states, if we consider now the massive case, so we have some interaction, and say we have one particle comes out, and we dress each particle. We have a massive particle. We put some Faddeev-Coolidge will dress it from soft photons, but photons go out to infinity. So the dressed Faddeev-Coolidge states, if you draw them on a picture like this, the cloud is a cloud of stuff that goes out to null infinity. And if you wait a long time, a long amount of retarded time, the charged particle loses its soft photons. They move infinitely far away. So in the discussion of Faddeev-Coolidge states, the language that is used suggests, wrongly, I don't think they say anything wrong, but I had this misimpression, and many people had the misimpression, that somehow this cloud of soft photons hung around forever with the charged particles, and we could think of them all as one unit. That is not what this cloud of soft photons is doing at all. What it is doing is shielding all the angular dependence of the Coulomb field. So if we look at this kind of situation where the thing goes out to infinity, we have a Coulomb here. In the massive case, there is no dressing which has no Coulomb fields anywhere. You have no Coulomb anywhere. You reach some critical point, which so the Faddeev-Coolidge construction is not Lorentz invariant. You reach some critical point which they take to be retarded time u equals 0. And at that point, there's a cloud of soft photons, which, so of course, a cloud of photons can never have net Coulomb charge, but it can move around the angular dependence of the radial component of the electric field. You get this cloud of soft photons, which sets the Coulomb to 0 or to a constant. I'm not interested in the constant mode. Once you pass this cloud. Okay, I think I'm not going to discuss what the shape of the cloud is for the massive case because I'm going a little bit slower than I thought. Okay, so now I want to make a conjecture, or we made a conjecture. So let's imagine we have some scattering amplitude. Oh, sorry, what happens in the Faddeev? How does the cancellation occur? Well, in Bhabha scattering, we have some amplitude. And now we have the clouds. And when we look at this exchange, which was infrared divergent, it's canceled by another exchange where you exchange a soft photon not between two charged particles, but between an external charged particle and the cloud associated with a second charged particle. And the sum of these things is IR finite. The leading IR divergences cancel. Now, these clouds can be moved around. They don't have to be exactly where the particle comes out. They could be moved around up to there. All that matters, and in fact, Faddeev and Coolidge don't even associate them with the position of the particle. All that matters is, in the Faddeev-Coolidge construction, is that they shield the Coulomb field at infinity. Okay, so this is very nice, but it's still a very limited thing because Faddeev-Coolidge states are highly unphysical. When we scatter two protons at the LHC, we don't follow it up with a cloud of soft photons with just the right profile so that you have a perfectly spherically symmetric Coulomb field at infinity. And certainly in the measurement at in any scattering experiment, in the measurement at LIGO, you have all kinds of angular dependence, been measured in many contexts, angular dependence of the leading term in the Coulombic field. So they're highly unphysical. So the Fadeev-Coolidge construction only tells us how to scatter a set of measure zero states, which are rather unphysical. So it's not a satisfactory solution. It's progress, but it's not a satisfactory solution of how we deal with divergences in gauge theory and in gravity. Now, what Fadeev and Coolidge already knew was that you could move these clouds around. You could move them up and down, scry minus, and you could do that by things that didn't affect the zero momentum behavior and therefore would not affect any cancellation of divergences. But now what we want to claim is, let me draw this picture a little differently, that let's say each of these has their cloud. We could take this cloud and move it like this and keep moving it. And when we get to the top of null infinity, we can actually move the cloud from the past to the future without affecting the cancellation of divergences. In other words, of course, once we get to here, the matching condition tells us that we want to antipodally match it, and we can move it up to here, to the antipodal point of where it was. And in this situation, now I've taken this cloud and I've moved it up to here somewhere. Take this cloud and move it up to here somewhere. And we showed that you still get a cancellation of leading divergences when you do this. The key is that all amplitudes must satisfy. This is all secretly just the soft photon theorem. The soft photon theorem relates soft photons to incoming and outgoing hard charges, and that is the basic conservation law. So as long as you satisfy the conservation law, you won't get in any trouble. So when I dragged this cloud away from the incoming particle, and so when I drag it to here, I now have Coulomb fields going up to here, and it's canceled out here. But once I drag it up to here, I now have Coulomb fields which extend all the way from here and come up to here. And so I'm no longer in a situation where the Coulomb fields at infinity all have to vanish. And in fact, the kind of endpoint of this logic is, in physics, what we usually do is we scatter hard particles and get out hard particles and soft radiation. So, anyway, but just to say, so we conjectured that if you take the clouds associated, the Fadeev-Coolidge closed stating with the incoming state, and move them to the outgoing state, that all infrared divergences will still cancel, and you'll get a finite scattering amplitude. We showed that the leading infrared divergence cancels. We didn't get into the woods of all the sub-leading diagrams, but these guys, Choi and Okuri, did that a couple weeks ago. And so now there's a proof that these amplitudes, which satisfy the conservation laws, you see in this example, it no longer has to be true that the Coulomb field vanishes at infinity, that as long as all the conservation laws are satisfied, that the scattering amplitude will be infrared finite. And the natural kind of endpoint of this is that to take, in real experiments, we tend not to have any incoming clouds. We just scatter hard particles. And some hard particles come out. When they leave the interaction region, typically some soft radiation is produced. And there's also soft radiation produced, which goes up to future null infinity when the incoming hard particles enter the interaction region. So these clouds, these Fedyaev-Coulomb clouds, are really nothing but the natural soft radiation that you would expect to be produced in any scattering process. So if we throw an electron and a proton at each other and they go out, there's some classical field that you just solved with the retarded Maxwell-Green function and that you would expect to be produced. And those are not Fedyaev-Coulomb states, but yet, according to these new developments, such amplitudes can be infrared finite. Okay, so now I guess, what time did I start? 9:40. I have 10 minutes. Okay, great. So no, in the real world, Bhabha scattering vanishes. Bhabha scattering is E plus E minus goes to E plus E minus with no photons.
Okay, but operationally, if you bang them together, there is scattering, and that is because you have the soft radiation coming out.
Operationally, what Fedyaev and Coulomb would have told you is if you want to have some sort of finite amplitude that's like Bhabha scattering, the best you could do, which seems to me very unsatisfactory, is to, well, either you can talk about the inclusive cross sections, and I guess I should also add that the inclusive cross sections are bothersome both, you know, if you want to talk about quantum field theory as a well-defined mathematical object in which unitarity, you know, you can't talk about inclusive things. And they're also bothersome for, if you want to talk about black hole information, because you have to worry about whether when you're tracing over something, you're throwing information away or not. So what Fedyaev, the state of the art was, according to Fedyaev-Coulomb, okay, Bhabha scattering is 0, but I can put some clouds here. I can define some state which I can make to be near the E plus E minus state, and that will be finite. But the new improvement is that you can take these incoming clouds, you can have Coulomb fields out here, you move them up, and you have some clouds up here, and such things will be finite. And what these clouds really are is the, you know, it's just the radiation that is inevitably produced when you scatter two charged particles. You can't scatter two charged particles without having some, you know, in a non-trivial way, without having some time dependence in the electromagnetic field and getting some amount of soft radiation. And you can show, I guess I didn't quite go through that algebra, but it should be obvious from the example, that whenever you have a non-trivial soft factor, as in the Weinberg soft theorem, which you do whenever you have non-trivial scattering, that there will always be some soft radiation and some shift in the vacuum. So up here in Bhabha scattering, the asymptotic vacuum is a different flat connection than the one down here. That's what the soft theorem tells us, that this difference between the initial and final connection cannot be 0 in any, so you cannot start and end in the same vacuum in any scattering process, in any non-trivial scattering process. Yes? Well, of course, there's no the people who work on the SCET people and so on, they compute many different things, so it's hard to generalize. But they're often computing a thing which will sum up to which will sum up to 0 if you add the exchanges in them. The Wilson lines are just the charged particles. They're the sources for the. But by the way, this is all completely consistent. Of course, it's all completely consistent because I'm not doing anything different here. I'm just saying different words for old physics, but they have not been using these kinds of states. Yeah. Then the soft stuff at Scri plus, and that's the physical situation. I mean, at the LHC, they don't say, well, what if there's some soft stuff coming in at the same time? Or at LIGO, they just assume, well, there was no soft stuff coming in. So those are the physical experiments. Okay, so let me just quickly say 2 things. One is that, all right, now there's some controversy is too strong of a word. But if somebody in the audience could resolve this for me, I would be very grateful. But I believe it's the case that there is no analog, at least, I guess I'm pretty sure it's the case that there is no analog of the Faddeev-Coolidge construction, which is universally accepted for non-abelian gauge theory. So we could be talking, of course, if it's confined or Higgsed, that's a different story. Then we don't have these conservation laws. But it's very natural to make the conjecture, and there you get infrared divergences all over the place. And it's very natural to make the conjecture that there's a conservation law up at null infinity that looks just like an awful lot like that. And so it's